Okay, welcome everybody to the video. Like I mentioned earlier today, I want to start off with chapter 5, number 26, in showing that the acceleration of the first mass in number 32 is actually double that of the acceleration of the second mass. But we have to, go back and make sure that we understand what's going on in a simpler system, like in number 26 of chapter 5. There we saw, after carefully designing our perspective and the XY plane for both masses, forming drawing the free body diagrams for both masses, and putting out the equations of motion for both masses, we found that the acceleration that we have in the system is going to be a common acceleration, that both masses are going to be moving with the same acceleration. They're going to be displaced, delta x, the same displacement. So they're going to move in the same amount of time, and they're going to achieve the same final velocity. And we've seen that in a couple of examples where we find the acceleration of the system, which is for both masses. Then we can use kinematics to find out how far they both traveled. It's not like one traveled one displacement and the other one traveled the other. They both travel the same displacement because they have the same common acceleration. And we know that those kinematics equations are built or based on common acceleration A. And therefore the time will be the same and the final velocity will be the same because of the common acceleration A. And we also, for many of our problems, we can assume that the initial velocity is equal to 0. So it starts from rest. So that's what we saw in problems of this type, like number 26. So number 32, if I was to say that this, in proving things, that this will be my step 1. And then my step 2 would just be what I know about the system from a problem like number 26. And the third thing we can say is that we can make a claim based on the information. The claim in the problem was that there's 2 accelerations. So there's A1 and A2 for mass 1 and mass 2. Right? Respectively. Then they said, okay, what is the relationship? Well, we then in class stated that the acceleration of the first mass is equal to double that of the second. And the position was that mass 1 in number 32 travels double the distance as mass 2 does, and so therefore it has double the acceleration. So that was a little bit iffy to visualize, maybe a little bit too intuitive, but it doesn't come from anywhere. So we're going to show that more definitively right now. So we can use the kinematics equations. Okay, delta x, 1/2 at squared, and that's why we know that a1 is going to be double the acceleration of a2. But let's do this a little bit more empirically. So like I said before, so again in number 26 of chapter 5, for the given acceleration A of that problem, we can find the common displacement for both, the common time for both to travel, the common final velocity of the entire system, etc. Why are these common? Because they're based off of the common acceleration A. Therefore, all of these will be the same. Okay. For a problem of that type. Number 26. Number 32, it gets a little funky. All right, so let's continue on with this one. So let's go back to stay with 26. So let's say just, I'm gonna just pick a number. It doesn't matter what it is. Let's say the acceleration we found in 26 equals 2 meters per second squared. And, for t equals 1 second. So it took 1 second for the whole system to start from rest and hit the bottom or stop moving. Then we can say that the displacement of both masses, the common displacement, be found in this kinematics equation. VI is equal to 0, so therefore that goes away. And we have 1/2 AT squared, and then we can say 1/2 2 times 1 squared, and that just becomes 1 meter. Okay. So let's say that all things being equal, we'll take the same two masses, or any two masses, if we will, with this common distance, and go to number 32. Now in 32, we have, let's see, so I'll try to start the mass one right here. And then so this pulley. And then what did we have? Okay, we had T2. This string is going to be common to the second mass, the second pulley. And the supposition or the claim for 32 is that this is A2. Let me see if I can. Better. This is A2 for M2. And then this would be A1 for M1. Okay, because that's the configuration. We could do an A3 to have the combination, but we're going to get all crazy like that. Okay. So let's say it's the same table, same mass, whatever the masses are, that's not really important. The thing that we know, and taking our claim from 26 or this scenario up top, is that the distance traveled by M1 is going to be 1 meter going in that direction. So let's say whatever the distance up top here, it's not to scale, but we're going to say that the distance traveled is the same as 26, or a given distance that we found here being 1 meter, or whatever this distance is. We're going to take that same distance in this new problem. So let's say that distance was 1 or whatever it is, then this distance up top will also be 1. So that's double the distance. The claim was that the accelerations are different, A1 and A2. But the entire system at the end is going to be moving in the same amount of time, okay, time t, and the final velocity being whatever that is. It's going to be in terms of the different accelerations, okay? So we can, make the claim, or just all things being equal, we have our time and our VF being different, or actually being the same for both systems. Even though the acceleration for M1 and M2 will be different, this guy is going to be accelerating more than A2. Let's say that the whole system is going to be moving uniformly in time and in velocity, if we were taking the system as a whole. So that's one thing that we can keep in the background. So this A1, A2 business, let's prove that the claim is true, that A1 is double A2. So for this distance here, this is 1, this is 1. So it's going to travel, say, 2 meters or double the distance. And our position up top here for mass 2 will be that it travels distance of 1, but D1 travels a distance of 2. It goes forward and then over, double the distance. Distances are different. Meaning D1 is greater than D2, it's actually double for M1 and M2 respectively. Right, so, oops. So as we said, as we can see, for any given distance, 2, 200, whatever the distance is, D1 is going to be double the distance of D2. Okay. So now to the A1, A2 business, because that's our point of contention in this problem. So using the equation VF squared plus 2AD delta x over the displacement variable you want to use there, we can then show that the claim is valid. Proving it. So solving for A1, we know that this goes away. Let's say that this is A1. We'll have VF squared over 2 times D1, 2A1 D1. Okay? And we know that D1 is double D2. A2 then will be VF squared over 2 D1 over 2. Okay, because this here would be D2. If we solve for D2, then D2 is going to be equal to half the distance of 1. D2 falls 1, and D1 falls or moves through 2 meters total. And again, the supposition of V final is the same, and we're going to treat the system as moving uniformly to end at the same time. But that's kind of separate, but contextually valid. We're not trying to, show anything different about VF or T, but that's what we can claim about that system, that the time and the final speed will be the same. It's just that the A's are different because of their different distances. Now we solve for A1 and A2 respectively. We can see that A2 is going to be double that of D1. So A1 is this, and then we just multiply both sides by 2, and so we're going to get 2A2 is equal to VF squared over 2D1. All right, or that, A2 or A1 is double A2. Same equation. And so that's pretty much the proof that A1 is double A2. Acceleration of 1, double acceleration of 2. I don't know if that was easier or whatever, hopefully a little bit more intuitive, a little bit more logical. But that's really what I was saying earlier, that the real reason that A1 is double is because it travels, the mass 1 travels double the distance of A2. May have seemed a little hand wavy, but again, this is a little bit more logical as to why that is. So hopefully that makes a little bit more sense, a lot more sense. And any questions you have for me, you can just put at the bottom of the video or email me or whatever. Okay. Talk to you later. Okay. Yeah, so one last thing, the implication or implicit nature of the problem is that in order for it to stop with the same velocity, same time, all that stuff, this must be the relationship of A1 to A2, that A1 is equal to double A2 in order for this equation to be the same. To have the same final speed, to have the same time, the system ends at the same time with the same final speed and all that. So in order for that to happen, this must be the relationship, and we just proved it so from the notions up top. All right, talk to you later.